Hi, in this lecture, we will discuss how to build a KEM, a key encapsulation mechanism, from the module LWE problem. So the outline of this lecture is the following. First, we'll define what KEMs are, then we'll define the module LWE problem. We'll show how to solve one way to solve module LWE with lattices. And finally, we'll introduce a construction of a KEM based on module LWE. So what is a key encapsulation mechanism? So in a key encapsulation mechanism, Alice and Bob are trying to end up in a situation where they share a secret key that they can use, for example, as a session key for a symmetric encryption scheme. So first, they rely. So the KEM itself has a public key and a private key. So it's itself a public key cryptographic scheme. So the first component of the KEM is key generation. So in this case, if Alice, so the situation is not symmetric. So Alice can be the one generating the keys. So she generates a private key and a public key. The green public key is being distributed for anybody. So Bob in particular is assumed to possess Alice's public key. Then the encapsulation is a procedure that is run by Bob from the public key. Bob creates a ciphertext and a key. Now Bob sends the ciphertext to Alice, and Alice, using her private key and the ciphertext, is able to decapsulate, and that decapsulation procedure returns the exact same key that Bob has. Now, the purpose of this, of course, is to end up with a symmetric key because typically symmetric ciphers are more efficient in terms of space and running time than public key cryptographic schemes. Otherwise, this whole thing is redundant with public key encryption. But we assume here that we do not want to use public key encryption because public key encryption is more expensive than symmetric key encryption. Now, what is the security game that specifies the security of KEMs? So the notion of security that we're interested in is indistinguishability under chosen ciphertext attacks. So in this security game, we have an adversary playing a game against a challenger. The challenger chooses the keys and distributes the public key, which is assumed to be available to the adversary. Then the challenger chooses, runs the encapsulation algorithm to get a key 0, so K0 a key and a ciphertext. And also the challenger chooses another key, this time uniformly at random in the key space. Then the challenger rolls the dice, flips a coin and decides, so draws B between 0 and 1, and gets the key of index B. So that could be key 0 or key 1, depending on the outcome of the coin toss. And then that key is sent to the adversary alongside with the ciphertext. Now, because it's a chosen ciphertext attack, the adversary has the opportunity to request, so to choose ciphertexts that are not the challenge. So any ciphertext that is not equal to the challenge, and request their decapsulation from the challenger. So the challenger has to send all the keys that correspond to the ciphertexts of the choice of the adversary. And then at the end of the game, the adversary needs to decide which key he was sent. So was that the key of index 0, which was created through an encapsulation operation, or was it the key of index 1, which was drawn uniformly at random in the space of keys? And if that's not possible for any efficient adversary, then the scheme has indistinguishability under chosen ciphertext attacks. Now, let's define the module LWE problem. So the parameters are a modulus Q, a number of samples M, a dimension K, and a distribution over Z sub Q of X quotient by x to the n plus 1. The input of the problem is samples of the form AI and the dot product of AI by S plus an error EI, where the AIs are drawn in ZQ of X quotient by x to the n plus 1 to the K. The EIs are drawn according to the distribution, and the goal is to find the secret S. So this is really an analog of the LWE problem, except that we've replaced elements in ZQ by elements in ZQ of X quotient by x to the n plus 1. So we can also express this problem in terms of matrices, where we're given the matrix A and the vector AS plus E. So let's just work it out in example. So let's say Q equals 11, N equals 3, K equals 2, and M equals 6. And the secret S can be, for example, so it's a vector of length 2 on Z Q of X quotient by x to the n plus 1. So for example, x plus 1, x minus 1. Now here is a matrix A. Then with that choice of vector E, the second component of the challenge is the vector B given by AS plus E, which is what you see here. Now, let's introduce one of the lattice attacks against LWE, which then will show how to turn it into a lattice attack against module LWE. But first, it's important to understand how it works against the traditional LWE problem. So let's assume that we have an instance of the LWE problem, so A and B, which is AS plus E. Now notice that this matrix vector multiplication gives you minus E minus T, where T is something you choose, typically small, so typically T equals 1. And that's just to make this a lattice of full rank. And then this vector minus E minus T is a vector of the lattice defined, is a linear combination of those column vectors, okay, defined by this matrix. So we can perform a Gaussian elimination on the columns of A. So remember Gaussian elimination from our lecture on the recap of linear algebra. We define it over the rows, but you can perform a transposition, do it over the rows, and then perform another transposition, or you can accept that we can replace all left multiplications by right multiplications, and that gives us a way to find a matrix U that is invertible, such that when we multiply it on the right by A, what you get is a block of identity and something else. So with that, we have that if we can rewrite that matrix plot here by inserting this identity, which is U and 1, and then multiply by U inverse and 1. And then if we perform this operation first, then this is the shape of the new matrix, and then multiply by this, which is a sort of an S prime and a minus 1, where S prime is directly related to S through a matrix multiplication by U. So we've just slightly changed our problem, where we show that we are able to replace the input A by a block of identity and A prime. Now, so now we assume that this is our challenge, finding S prime that satisfies this identity here. Now, previously, all our matrices were over ZQ. Okay, but now assuming that we're dealing with lattices, we're gonna have to turn this identity into an identity of matrices over Z. And in particular, we need to take care of the modular reductions. So see, when you have this matrix multiplication with matrices over ZQ, then implicitly you have all the modular reductions taken care of. But now if you take representatives of these matrices over Z, that identity is no longer true with matrices over Z. It's true up to an addition by a vector of coordinates that are a multiple of Q. okay, that takes care of the reductions modulo Q. Okay, so so that's now what we're looking for. We're looking for a short vector, right? Because E is short, so really we want a short vector in the lattice whose columns are the who is defined by the columns of this matrix B here. Okay, and a short vector in that lattice is going to be given by minus E minus T or ET. Now, this is only heuristic in the sense that if that lattice had other short vectors, then we might hit them and not get a vector of the form ET or minus ET. But if E is chosen sufficiently small, then this vector in the lattice who's generated by the columns of B is going to be a very unusually short vector for a lattice of this volume. And so if the other vectors are significantly longer, then we can hope to find our vector easily. Now, I mean, it won't be easy to find the vector, but at least if we do, then it will answer our problem. So a vector, a short vector is going to be given by these elements, so the S prime, the -1, and whatever K that satisfy this identity. And once we find this, so we typically will get either minus E minus T or ET. And once we find that through a short vector search, then we have E, and with E we can take our instance AS plus E equals B, shave off the a term in E, and then what we have is AS, and that is through Gaussian elimination we can recover S. We call that learning without error in our recap of linear algebra. So let's work it out on an example. Let's say n equals 4, m equals 7, and q is 1009. Now let's generate a matrix A at random. Let's pick a vector E that is short. Remember, so the encryption with LWE works only if E is somewhat short. And then let's grab a vector S uniformly at random. Now AS plus E is this, and so the challenge is given by A and B. E and S are secret. Now our modular Gaussian elimination on the columns yield this matrix. So here is our identity block, and this is the block of A prime, which is not 0. Now, if we construct the matrix B as instructed before, then this is what we get. So we have our identity block here, the block of non-identity. We have B, we choose T equals 1, and then we take our diagonal component here of Q times the identity, okay? And a short vector in this lattice is exactly E and concatenated with 1, okay? So that's what you find if you call, for example, a matrix, lattice reduction technique such as LLL on this the Euclidean lattice generated by the columns of this matrix. What you get is this concatenated with 1, okay? And that gives you immediately E, and then you can get A times S and then perform Gaussian elimination and recover S. Now, this was to attack LWE. So to go from module LWE to LWE, we use those circular matrices that we discussed in our lecture on modular polynomials. So remember that the multiplication by a polynomial, mod x to the n plus 1, can be represented as a linear map where where the polynomial is identified by an n times n matrix, okay? Now, we can also take the matrix A that is given by, so it's a K by M matrix. So here is a 2 by 2 matrix over ZQ of x mod x to the n plus 1. And so each each coefficient can be replaced by a block that corresponds to the circular matrix of the multiplication by the element, the map of the multiplication by that element. So for example, here x corresponds to this block of the circular matrix of the multiplication by x. So remember this with the identity block here and the -1, or this one, x plus 1 here, we find it here. So x plus 1, so we have that first column, which is exactly the coefficients of x plus 1, then a shift of that, and then another shift, and then all the coefficients that pop up on the other side are with a minus sign. And you take b, so which this time is just a vector, and we replace b by the coefficients of the elements. So for example, here that 1 becomes a 1, 0, 0, and that 2x squared plus x minus 2 becomes a minus 2, 1, 2. Okay, and we can call that b prime and this a prime. And so the module LWE problem is given a secret S and an error term drawn according to a certain distribution, and A and AS plus E equals B. So given B and A, find S and E. Now, this can be rephrased as given A prime and B prime, find S prime and E prime that are in correspondence with S and E. And so here everything is in Z with coefficients in ZQ, and we've reduced our problem, which module LWE problem, to a matrix problem in ZQ, which corresponds to LWE, and that can be solved with the methods that we described before. Now, let's see how we can define first a public key encryption scheme from module LWE, and then from that we'll define a KEM. So the public key encryption scheme, in that public key scheme, we have Alice. So the public parameters, first of all, are this ring. So we'll use R instead of ZQ of X mod X to the N plus 1 in the interest of conciseness. And then we assume that we have a distribution over R. Okay, so in the key, a key generation process, Alice generates a matrix A in R to the K times K, and draws S and E according to the distribution chi. So we assume those to be small enough. And so the secret key is S, and the public key is A and AS plus E, which has been also denoted by B. Okay. Now, Bob wants to send a message to Alice. So the message M is a string, so a bit string of length n, where n is this n here, so the degree of x to the n plus 1. So this can be mapped to the class of a polynomial. So the class of the polynomial sum of the mi to the xi in zq of x mod x to the n plus 1. Now Bob draws R in E1 and E2. So R and E1 are vectors of over K of length, over R of length K, and E2 is drawn in R. And the ciphertext has two components: a vector, which is R times A plus E1, and an element in R, which is R times AS plus E. So this is a column vector, and this is a row vector. Okay, so this all together is an element in R, plus E2, which is drawn in R, plus the message times the rounding of Q over 2. Now Alice, to decrypt, first notices that V, so V is of the form the sum of the Ri Ai times S plus sum of the Xi Ei plus E2 plus the rounding of Q over 2 times M, and this is what U looks like. So putting this all together, this means that V minus U times S is of the form sum of the Ri EI plus E2 minus E1S. So this is altogether an E prime, which if the distribution was chosen carefully, will be of coefficients less than Q over 4, okay? And that all depends, of course, on the nature of this distribution here, in which we've left, deliberately left ambiguous, but this would have to be it would have to be very important to choose a distribution that ensures that this is small enough. And if the ith coefficient of this element of R is less than Q over 4, then what it means is mi equals 0, okay? Because we have ourselves an approximation of 0. And if, on the other hand, the ith coefficient is greater than Q over 4, then what it means is mi equals 1. Now, how do we get from public key encryption to a KEM? So the encapsulation, so we, first of all, the key generation remains the same. And the encapsulation works as follows. We draw a message at random, and we hash the public key and that message to get k hat. Now, we encrypt the message with the public key. That gives us a ciphertext, and then we hash k hat and that ciphertext, and that gives us the key k. So the result of the encapsulation is this key k and this ciphertext c. Now, to decapsulate, assuming I'm sorry about the typo, this should be a secret key. So we do the decryption of our ciphertext and retrieve M. Then from M and the public key, we can hash and get k hat. And then from k hat and the ciphertext, we get k. And at the end, we both players share the key capital K. And that gives us, then they can engage in a private conversation using K as a session key. Now, in 2022, the NIST has standardized the Module LWE based KEM Kyber. So Kyber is based on the algorithms that we presented in this lecture with certain, so first certain special choices. So Q, the modulus, is a set value, N has a set value. So that allows, so only K, the parameter K, is changes to increase the security. So that allows ring operations to be optimized once for all. So for the particular Q and the particular N that's been chosen. And then if one needs to increase the level of security, then one only increases K, which does not affect the nature of the ring operations. Now, there are certain subtleties in Kyber that we did not present, in particular the use of compression functions. So elements are not transmitted as we described, but rather they're compressed with a little bit of loss of information, which influences the errors and the probabilities of unsuccessful decryption. The distributions also are specified to binomial distributions, and we deliberately left that vague in our, the choice of the distribution. We left an open-ended choice in our description. So thank you for listening. So this was the aim for this lecture was to give an idea of how to make KEM based on Module LWE, and the objective, of course, is to give you guys an idea of how the NIST standard based on lattices for KEM works. Thank you very much for listening.